Okay, guys. So at the end of the last video, we saw how we came out of the gap DH reaction with 2 moles of 1,3-bisphosphoglycerate, right? This high energy compound over here that's going to become really important for the rest of this pathway. All right, so in reaction 7, we finally, like I said last time, we get something back. So we're going to take molecule of this 1,3-bisphosphoglycerate, right? And we're going to take some, let's go and write this down here. Take some ADP, right? And we're going to use the high phosphotransfer potential that we've discussed, the significantly higher phosphotransfer potential of that phosphate group on 1,3-bisphosphoglycerate to do a so-called substrate level phosphorylation event. Essentially, we're going to directly synthesize ATP from ADP by transferring that phosphate group right there onto the ADP to directly synthesize ATP, right? So our products then are going to be, this guy, which is of course 3-phosphoglycerate, right, or 3-PG plus ATP, right, which is awesome, right, because that's sort of what we were after. The enzyme that runs this reaction is, of course, phosphoglycerate kinase. Or PGK, right? The free energy change for driving this reaction, standard state free energy change, is pretty favorable, right? It's already quite favorable, right? Delta G naught prime, because we can exploit the free energy of that acyl phosphate. Remember, that has something like a 60 something kilojoule per mole hydrolysis free energy to make that ATP. So the standard state free energy change here is something like minus 18 kilojoules per mole. I don't know what the cellular condition I couldn't find it when I was looking these numbers up, maybe out there. It's certainly going to be much less than 0. It's probably significantly less. It's probably less than 18 kilojoules per mole, but I don't really know what it is, right? But it's going to be at least as favorable as the standard state free energy, probably significantly more so, right? Okay, again, like I said, this is a substrate level phosphorylation event. We're doing a basic group transfer from the 3-phosphoglycerate, 1,3-bisphosphoglycerate onto ADP to create our product ATP, right? Okay. Now, if you think about the energy balance up to this point, remember in our energy investment phase, to make fructose 1,6-bisphosphate, we had to burn 2 ATPs, right? Well, at this point, remember again, this reaction is going to happen twice, right? We're going to put 2 moles of 1,3-bisphosphoglycerate through the PGK reaction, and we're therefore going to make 2 ATPs, which means at this point, at reaction 7 in glycolysis, the pathway is energy neutral. We've completely paid for the energy investment phase, right? Okay, so now it's time to get something back. This is where we get our energetic profit back from this pathway. We set things up. Now it's time to get something back. Because if it's just neutral, we haven't done much good. We need a payoff. All right. Well, take a guess at where that payoff is going to come from based upon the molecule that's sitting there. We just did one substrate level phosphorylation event. I'll give you a hint. We're going to do another one. And we're going to do it with that phosphate, right? The one that's sitting over there on that 3 carbon. Okay, but the problem at this point chemically is that the phosphotransfer potential of that group, in a word, sucks, right? It's nowhere close to what you need to make ATP. So we got to do something to pump up the phosphotransfer potential of that phosphate group so we can use it to make ATP, right? And the question is, how do you do that? Well, the logic of the remaining steps of this pathway are centered around making that happen. And it's going to involve moving that phosphate group and then doing something to this molecule that makes the subsequent phosphoester super unstable, which we can then use to make ATP. All right, so let's see how that gets going. Now in reaction 8, we're going to begin that process, right? All right, so reaction 8 of glycolysis. We're going to take that 3-phosphoglycerate molecule, right? This is a really easy one to remember. Whoops, look at me writing out alcohols. Jeez. Right, and we're going to take this phosphate group and we're going to move it up here to the 2 position. All right, that's all we're going to do. So we're going to take 3-phosphoglycerate, 3PG, right? And we're essentially going to isomerize this molecule by just moving that phosphate group from the 3 position to the 2 position to make 2-phosphoglycerate. Or 2-phosphoglycerate, I'll just spell it out, be consistent. Or 2PG, right? Okay. The enzyme that runs this reaction is known as an isomerase, it's known as a mutase. It's called phosphoglycerate mutase. At least in the enzyme nomenclature that I was taught. And so I'm going to keep calling it phosphoglycerate mutase. Sometimes the names of these enzymes get changed, but we're going to stick with mutase. Okay. The standard state free energy change for this reaction, okay, we're coming back to this theme again, we've seen it several times, is not favorable. It's plus 4.6 kilojoules per mole. So just like so many of the other reactions, the aldolase reaction, the phosphoglucose isomerase reaction, the phosphoglycerate mutase reaction is not favorable. Now, again, this is another reaction where I have not been able to locate accepted value for the cellular condition free energy for this reaction. But again, for this reaction to go glycolytically, this is going to have to be less than 0. I just don't know the magnitude of it, right, under cellular conditions. Okay, but it's another situation where this equilibrium has to either get pushed by the flux of 3PG coming in, or pulled by the depletion of the concentration of 2-phosphoglycerate. There's one interesting wrinkle to this reaction. Phosphoglycerate mutase, the key active site residue in this enzyme, is a histidine, excuse me, which means what's going to happen for this enzyme, we're going to form, as we run this mutase, it's like essentially a isomerization reaction, we're going to form a phosphohistidine bond, right? It's not that common. Bacteria use this a lot in signaling systems. But for doing sort of intermediary metabolism like this, forming a phosphohistidine bond is not so common, but it's right at the center of the phosphoglycerate mutase reaction. Even somewhat more interesting is the fact that for this enzyme to work, it has to be prephosphorylated. And more specifically, there have to be catalytic amounts of a diphosphorylated version of phosphoglycerate, specifically 2,3 bisphosphoglycerate. So essentially the way this enzyme works is you have to have PGM, the enzyme. Oh, I forgot to write that out. Sorry, let me do that. The acronym for this enzyme is, of course, PGM, right? So you have to have PGM that has that phosphohistidine already formed, right? Then you bring in 3PG, right? Your substrate here. And in the active site of the enzyme, transiently is formed this PGM bound 2,3 bis phosphoglycerate. Come on. 2,3 bisphosphoglycerate, right? Which then will decay to yield the enzyme PGM plus 2-phosphoglycerate, right? So the wrinkle here is that the phosphate group that comes in on the 3-phosphoglycerate is not the phosphate group that leaves, right? The phosphate group that comes off over here is the phosphate group that was on the enzyme to begin with, and the one that came in is left behind on the histidine, which is why you need 2 catalytic amounts of 2,3-bisphosphoglycerate to get this enzyme to run. Because if it's not pre-phosphorylated and you only bring in one phosphate group, the reaction won't work. Right? Okay. All right. So we've made our 2-phosphoglycerate. We've moved the phosphate over. Now we got to do something to crank up that phosphotransfer potential. Right. This is in some ways the secret. Well, moving the phosphate over is important, but figuring out how to crank up the phosphotransfer potential is at least as important. And in this case, it involves a reaction that looks something like this. So I get this as reaction 9 in my schema here. We're now going to take that 2-phosphoglycerate molecule, right? Put that, there's that phosphate group. So 2PG, right? And we're now basically going to run an alpha beta elimination of water across this bond right here, right? To generate a molecule we've also talked about a little bit before. I'm going to put in a carbon-carbon double bond by dehydrating for that alcohol group and a proton from carbon 2, right? To generate phosphoenol pyruvate. Or PEP, right? The enzyme that drives this reaction is a sort of famous enzyme known as enolase, usually abbreviated ENO, right? Standard state free energy change for this reaction is, not so favorable. Again, here's that theme again, right? Standard state free energy change for these reactions, many of these reactions is not great. This one's only barely unfavorable, plus 1.7 kilojoules per mole, right? But under cellular conditions, by depleting the PEP pool, of course, here's that theme again, we pull the reaction in the forward direction, in the glycolytic direction, minus 3.3 kilojoules per mole, right? All right. So that's how we get this reaction to go. Again, as I said, the enolase reaction is basically doing is running an alpha beta elimination of water. Right, or across that 1,2 bond by popping this guy off and a proton here to generate that carbon-carbon double bond. So this would fall in that category of sort of that limited chemical toolkit we talked about, a functional group removal, right? As you recall, that often involves additions to or formation of carbon-carbon double bonds, right? So here's an example of that type of chemistry. All right, now you may also remember that PEP is super unstable. Its phosphotransfer potential is even higher than that of 1,3-bisphosphoglycerate, right? So this phosphate group here on phosphoenol pyruvate really, really, really doesn't want to be there. And the question now is why? If you think about it, why? and we moved the phosphate group over, and we just stuck that carbon-carbon double bond. Why would the phosphotransfer potential for that group now go up to something like minus 60 something kilojoules per mole, right? Okay. Well, if you think about the analog of this molecule, phosphoenol pyruvate, what if we had this molecule and it looked like it was just like a ketone, all right? Pyruvate. It just looked like that. You guys remember, I've mentioned it a few times, hopefully, that the protons, these protons on that methyl group are more acidic than a normal sort of methyl group because they're alpha to that carbonyl group. And that ketone will form an enol structure, right? That looks something like this, right? But guess what? Guess where that equilibrium lies? This will happen, right? But this molecule really does not want to look like that, right? This can happen, but this equilibrium lies so heavily in this direction that there is a dramatic, well, or very large thermodynamic driving force for this molecule to exist as a ketone, not as an enol, right? This is extremely unfavorable conformation of this, or state of this molecule. Okay, look at that molecule. Look at this molecule here now, that phosphoenol pyruvate. It's got the carbon-carbon double bond. It's got the oxygen there. This really, in principle, would want to isomerize to form a ketone, but it can't because that phosphate group's in the way. Until you get rid of the phosphate group, you cannot isomerize this molecule. It's stuck. It's trapped in this high energy state that is super unstable unless you get rid of the phosphate group, which is why the phosphotransfer potential, or the hydrolysis free energy of that phosphate group in phosphoenol pyruvate, is so favorable, because it's driven by the energetic drive to tautomerize this molecule back into a ketone from this enol group, right? Okay. So, and that is essentially what the last reaction of glycolysis is going to exploit, reaction 10. Is now going to take phosphoenol pyruvate, and we're going to do our second substrate level phosphorylation to make some ATP, right? So we'll take PEP, proton, some ADP, and we're going to make pyruvate and ATP, right? By transferring that phosphate group onto the ADP. The enzyme that runs this reaction is known as pyruvate kinase. Or PK. And you might think about that for a second and go, well, why is it called pyruvate kinase? Don't kinases phosphorylate things? Why is it called ATP kinase? Right? It's running in the opposite direction. We're making ATP by yanking the phosphate off phosphoenol pyruvate. And the reason is historical, that the enzyme was first discovered running in the opposite direction. Remember, there's no reason. Enzymes don't run one way, right? Enzymes just get you to equilibrium faster. And if you didn't have any phosphoenol pyruvate, you had lots of ATP, and you had lots of pyruvate, which I haven't written out here, right? You could drive that reaction in the opposite direction just fine. In fact, you know, it's not so easy. You take a lot of a fair amount of ATP and pyruvate for this to happen, because the standard state free energy change for this reaction, finally, we get another one that's super favorable, minus 31 kilojoules per mole, right? And under cellular conditions, it's actually not quite as favorable, 17 kilojoules per mole, because of the relative concentrations of ATP and pyruvate, right? But it's still pretty doggone favorable, right? Okay, so that's the end. That brings us 10 steps into glycolysis, all right, to the point of taking glucose and turning it into this 2 moles all right, 1 glucose into 2 moles of pyruvate. So it's worth sort of pondering for a second. How'd we do, right? Let's think about what's the balance sheet of glycolysis look like in the end. So we had 1 glucose molecule plus 2 ADPs. Let's just think about this sort of from the sort of gross production, right? I'll come back to the overall balance in a second, but just from what was actually produced, plus 2 inorganic phosphates, plus 2 NAD pluses, and that gave us 2 pyruvates, plus 2 ATP, plus 2 waters, plus 2 NADHs. Doesn't seem so awesome, right? Really? Just 2 ATP? But, right? These guys, oh boy, remember our high potential electrons, right? Remember those? These guys can be worth 3 ATP each, which means they're equivalent to 6 ATP from that one glucose, right? It's just through glycolysis alone. So, and if you look at the sort of net, right? If we just, consider the whole production and we take out the ATP we had to expend, right? Which, just consider what our actual balance would be from 1 glucose, subtracting out the cost, we would have 8 ADP, right? Again, subtracting away the 2 that we had to expend. We're just looking at what our sort of net result would be, plus 8 inorganic phosphates. Plus 6 protons, plus something really important. There's a key thing for this to work, right? Let's just write this one out. We would get 2 pyruvates, right? Plus 8 ATP, if you sum all of this up, right? Here and here, plus 8 ATP, right? Plus a fair amount of water, 10 water molecules, right? That's really good. There's only one little problem. To get that yield, you need something else. You got to have oxygen. If there's no oxygen around, you don't get these guys. Without oxygen, all you get are 2 ATP per glucose. And to see why, we'll explore that issue in the next video.